Today we will start our lectures from considering the topic of tensors. We not going to go into the extended theory of tensors and their manipulations, but we'll try to introduce the basics, minimums that we would need to go on with our considerations of the mechanics of nonlinear materials, of these soft materials. So, in many ways, though, this you're already familiar with the concept of tensors, and you used some of them from different orders, and such as I'll talk about that very briefly, and soon. So you know scalars, vectors. You also multiplied some matrices, and so that is in many ways will be connected to what we talk today. So there's of course lots of literature on this topic that goes in depth in this consideration. Now let's why do just to pose this question that why would we need this tensors? That's basically for us define a convenient language for us to describe things. So, and I will give you a few examples, especially what we would need, what we'll use here, right? So things that you are familiar with, so that let's start from scalars that you already know. A few examples that can be energy, temperature, pressure, right? Actually, pressure is a good question, whether we would treat it as a scalar or is that something else. Is there any concept of directionality here, or this is just a number, right? So scalar basically doesn't have anything that is related to the direction, right? So it's opposite to vectors. It's just a number we can measure it at any point, right? And then it can be different at different points, can be the same. There can be gradients between these measures in different points, especially. But in general, it's just one number that describe the property at a particular point. Now, for again another familiar concept for you, it's vectors. I'm sure you had some experience with that, manipulating, multiplying it differently, and this is a very intuitive concept, right? So when we have a quantity, say force, as in examples here, or velocity, so it's clearly it has a directionality, so there is a direction in which it acts, or velocity that it goes in some direction, or acceleration vector that tries to change the velocity in a particular direction, particular point. Again, all of this also can be function of the coordinates, so they can be differently spatially distributed. Think about the fluid mechanics, the velocity may be different at different points. There will be gradients and velocity too. Now this is something that you're very familiar, also very intuitively understandable concept. So one important note that this is again just defining our language, so we'll understand each other better of what is written in the books or in journals. It will be understood connected more clearly. Is that typically the convention is that we use bold as I indicated here for as I indicated here, so for these quantities that are not scalars. So scalars will be some italic or some just letter, and if we want to emphasize that this is not a scalar, this is a first or second order term, higher order tensor, so we'll use bold or something else, but then we'll specify otherwise. So that's important to remember, that when we have a number, just a scalar, so this will not be bold. If you see bold, so the tensors, and you need to apply all the machinery that is related to tensors. All right. Next is our next thing is so we can increase the order. So we actually could say scalars would be our zero order tensors, which numbers. Vectors is the first order tensor, and now we're going to the second order tensor. Tensor is just examples for us, and this will be very familiar for us from mechanics of materials, so other basic courses. the so-called strain and stresses, right? So like you remember, in strain and stresses we had the matrices, right? So we had nine entries there. So we have matrix 3 by 3 in 3 dimensions, and so we didn't treat them as tensors yet, but there's something that is already very close. So what we actually dealt with was the components of stress. And as you can see, of course, as you can think about the difference between the vectors and the second order tensors, is that it's for vectors that was enough for us in a way to say that there's one direction would define that quantity. So with second order tensors, you will have an increased space that defines these so-called directions for the stress, right? So again, you can visualize that example of a stress that acts on a certain phase, and phase has a normal, so one direction, and also the force that acts on that phase also has its direction, and these two combined, the direction of the phase, the normal to the phase, and the direction of that force that acts on that phase, that would define for us back then the components of stress. And so that's so there are two directions in a way. So I think it's a good beginning for us. In a more abstract manner, a second order tensor you can think would be something as you can actually think about it as an action. So it acts on a vector and transforms that vector into some new vector. Or as one of the examples of that classical that you manipulated in mathematics or linear algebra, is where you had the eigenvalue problem, and that's where you had the matrix, right? So, but that can be thought as a tensor that acts on the vector, which in that case was your eigenvector, and it transforms that into the same eigenvector, but scaled somehow, multiplied by a constant. So again, this is just an example of this particular case when that happened to be the eigenvector, so that was transferred to the same eigenvector with increased length or changed length. But in a way, again, the tensor would be just something that transformed one vector into another vector. So this can be thought as an action, as is something that maps vectors. Okay. All right. So and we can increase, and we can have third order tensors. We can have fourth order tensor, and I will give one natural higher order tensor example as a tensor of elastic modeling, and that is actually a fourth order tensor. And we would need that to properly connect stress and strain. So if stress is second order tensor and strain is second order tensor, and we think about that in terms of the components, and we want to in general allow all the components depend on each other, because for example a material can be very complicated, and if we apply force stress in certain directions, certain stresses, you would expect from complicated material possible that deformation will be, or you apply deformation, then you expect stresses developing in other direction. Depending on the complexity of the materials, that could be possible, and mathematically, of course, that can be allowed, and that would be done through the fourth order tensor. So fourth order tensor will allow us to connect all the components in stress to strain. And this is just again an example for us for application for what we would be dealing with, and this is stresses and strains. But this is, of course, it's much more generic and used in many other fields, not only in mechanics of material or mechanics of soft materials. All right, with this very brief, maybe a little bit extended introduction of tensors, let's go back to our simple, the first one, so that has directionality. Scalars will assume that is trivial, and so we jump towards vectors. Again, the example would be force or velocity, and so now let's just look again into what we have here, right? So to introduce the vectors would be for us, of course, convenient to introduce a coordinate system. So let it be a Cartesian coordinate system, and we have a combination of these so-called mutually orthogonal basis vectors, right? So let's say that the unit basis vectors, so the length of each of these E1, E2, and E3 will be so the E1, E2, and E3, they are unit vectors, and they're also orthogonal. So there's 90 degrees, they're perpendicular to each other. And so they basically build our Cartesian coordinate system. Now, so now we are interested in defining these vectors through in this coordinate system, right? Okay, so we already said that our vectors are unit vectors, so basically the projections of this will be, for example, E1 will be projected so on itself, and x1 it will be only 1, and there will be 0 projections on x2 and x3, and so then we can write them as coordinates as we usually do in again linear algebra. So that's where you have this type of writing this in this manner. So these are indeed components, right? So and again, so the I try to emphasize it here. So so A and B were denoted as bold, as well as these unit vectors, because they are indeed vectors, but components here are of course scalars. And this is important notion. Now, then, if that's the case, so we can write A in this coordinate system is a linear combination of these based on our basis vectors, right? So there we have these components. So this is A1, A2, A3. They form a vector coordinate, or basically our components, right? So, and as you can see, it's a linear combination. So it's basically our sum. We have a summation here of this, and so we many times you don't want to write it like this. So you you can use the usual summation sign and indicate that you're in 3 dimensions. So I runs from 1 to 3, and so this is the this sum of these i's in here. One important notion here that is adopted in lots of scientific literature is the so-called Einstein rule, or index summation. This will be very important to adopt and use it again in books and in literature. In many cases, it even goes without mentioning or saying that, and that may be confusing if you are not familiar with that. But again, once we introduce it here, so you can know and start using that. So one can joke that so what we want to do is just to write less and save on ink a little bit. And so what the rule is that instead of writing this big summation sign and indicating how we sum this on I, we actually say, okay, anytime when I see that I have these repeated indexes, so that would mean for me a summation and cannot be anything else. If it's anything else, I will need to explicitly say that. Otherwise, everybody who reads that will think that I mean here a summation. So double I here means that whatever number of I you have, you need to sum all of them if they repeat each other. And so this is due to our dear friend Albert Einstein, so that gave his name to this rule. And in his work, he worked a lot with index notation. That, of course, helped him to shorten and see more clearly in the picture behind the formula. So notation sometimes is important in many cases because that basically our language and helps us understand things. All right. One more comment on that is just sometimes can be referred as a slang, but these indexes are called dummy indexes. So these that are repeated, they are dummy as opposite to the free index. So the free index, when you don't have a summation that has an actual meaning for the other components, well, these are not free. We need to essentially, if we write it explicitly, there is no index at all, so the dummy index, right? So because there is already, when we write it I, so there is no freedom in choosing I, so it has to be like the summation, like here 1 1 2 2 3 3. We cannot do anything else. So these are not free indexes, and they are called dummy indexes. And as a consequences here is that our choice of a particular letter here, either I or any other letter, J, J, M, M, doesn't change the meaning of that. So once we have two identical indexes, then immediately we need to write this as a summation. Oh, we don't need to write, but that's what exactly the expression means, and that's what we understand by that. So it doesn't matter what letter it will be, the the translation to its meaning is just this is sum 1 1 2 2 3 3, and they are not free. That's partially that's why they are called free indexes. All right, so with that, let's introduce a scalar product. Again, so this is not something that you're not familiar with, so this is something that already was considered, right? And the meaning for that is, all right, so basically we are, with this scalar product of vectors, what we're doing is we are calculating the projection of one vector upon another, right? So this is a projection operator, and as a result of this scalar product is that when we multiply two vectors, the result will be a number, so it will be a scalar, and hence the name of this operation. However, this scalar product, the so-called here is, you see the dot to indicate the scalar product, also can be thought of when we multiply tensor with a vector. So there, and sometimes instead of that, because the result is not a scalar product but something similar, so it's called dot product. Now, what happens with that dot product is that this multiplication leads to the reduction, one order reduction in the order of that tensor of any order. So, for example, here we had our vector, which was a first order tensor, and we as a result of the dot product, of the scalar product, the order of that first order tensor reduced to zero order to scalar, right? And and in similar manner, when we apply, we will try to multiply tensors by dot product with vectors, so the tensors of second order will reduce to first order. And again, very similar, that's what we already have seen, is that in the eigenvalue problems that I already mentioned to you, when you tensor multiply the vector, again dot product, and the result is another vector multiplied by some scalar, so we reduced the order. Okay, anyway, so now what we wrote here so far is the following. So we just started from this dot or scalar product of two vectors A and B, and then we explicitly wrote them in terms of their components. So we have this AI, EI, right? And again, you can see that AI are components, so that they are not bold, these are numbers, right? So, but EI is a vector, indicates that it's bold, so it's a vector. So it's the same with EJ, but BJ, of course, not a vector, so it's not bold. Now, so this dot product indeed applies only to the tensors or to the vector. So these scalars AI and components BJ can be pulled outside. They are not affected by this dot to dot product, so they're just staying outside. One more note here, as we wrote this, choose the letters, and you remember because these are dummy indexes, so we can choose any letter for that. It could be an N, MM, or whatever you prefer. But important thing to do here is not to write the same II here, otherwise we don't explicitly know which of them we need to sum up, right? So we could, if we write here instead of JJ, II2, so then we could confuse what are actually what is the summation here between which of these repeating indexes. So when we write that, okay, let's keep it simple for us, not to confuse anybody. Okay, so we pull these scalars outside, and now we need to deal with this EI, EJ dot product. But basically what it is, again, what is scalar product, is a projection, and projection one on another. And then what would that mean is that you remember that we said that they are mutually orthogonal vectors, right? So this is our basis, unit basis for the coordinates. So basically, if we try to project them on each other, so the only cases when there will be non-zero is when we project these vectors upon itself, right? So when again here, so just to remind you, so when we calculate this dot product, so only this that will project on itself, E1 multiplied with E1, so that will be 1, or E2 E2 or E3 E3, so only this will produce as number 1 unit. Others will be just 0, because of course there is no projection on, say, E1 on E2 E3, so it will be 0 projection. That's a definition of what we call the mutually orthogonal. And hence we can write this and give a name for that symbol that we'll introduce here. We can write that the multiplication of the dot product of EI, EJ can be either 1 or 0, and 1 when I equal to j means that we are projecting the same vector upon itself, unit vector, and 0 is any other combination where we're trying to project it on his neighbors, but of course that will be 0. And to write that is more compactly, so we choose I choose this symbol. It's just called Kronecker Delta, in the name of Leopold Kronecker, another scientist that worked a lot in the area. So, and call it delta ij. So in fact, the structure of this delta ij is such that it's very similar to what you've seen in this identity matrix, right? When we have 1 only on the diagonal 1 1 2 2 and 3 3, and there is 0 otherwise out of the diagonal. That's exactly what it will be in the matrix form when we try to write delta ij. Okay, so alright, so let's return to our scalar product. And with this new notation of Kronecker delta, let's write our expand and write explicitly what is the result of a scalar product with two arbitrary chosen vectors a, b. So didn't say anything about them, so they just some vectors. Okay, so that we already figured out, so we can pull the components outside just to making sure that we keep the indexes. So after that we will know what to do with them, what will be the resulting scalar of this multiplication. Indexes will be important. Now we already looked into this dot product of these two basis vectors, EI, EJ, so this combination, so this again a projection, and so and concluded that we can replace it by a more compact results as a Kronecker delta. So EI, EJ, the dot product will be delta IJ. So now I'll just replace it, and so we have AI, BJ, delta IJ. And here comes an important property of Kronecker delta. And the property is such that when delta multiplies some quantity in which the index, one of the indexes is the same as what delta has, so delta acts on that quantity here and basically just replace the index with the remained one, seemingly free index here, right? If we consider only multiplication bj delta ij. So basically all this is converted to bi. So I come and see that delta has j and b also have j, and so then what I do is I just replace this j with I and nothing happens. And we can look into how it happens again. So again, this is comes to the property of delta, that is only will be 1 when I equal j, and will be 0 if anything else. So then we can replace here ai with bj with bi, right? So but in a way we also could do exactly the same here. If we notice that delta has the same index as I, here is a here, so we have we can come and say delta will act on a, and so it will replace I here with j, so the one that was free in this combination a and delta, and so then we'll have aj bj here. So another way to write it, but as we already know, so these are dummy indexes, so it can be ii, jj, or you can even replace them with any other. So it just means that we have a summation that we need to run it over jj, and depending on our dimensions, so that will be in 3 dimensions, so we have 3 terms there, a1 b1 plus a2 b2 plus a3 b3. And as promised, yes, so that's what you expect. This is a scalar, there's nothing bold here in the result, and we started from the scalar product of 2 vectors, so of course we expect a scalar as a result. Now we can look into that again, into that multiplication bj delta ij, and so and if we look into that more closely, so again let's use what we learned already, is that we have dummy indexes and free indexes. A little bit can exercise it here. So the dummy indexes is jj, so this is repeating, so that means that we need to create a summation while I is still it's a free index, right? So when I write it explicitly, so I'll have b1 delta i1 plus b2 delta I2 plus B3 delta I3, exactly that, right? So this is the summation. So I is still a free index. Now, for example, now I would like to write a component of this multiplication that I will be equal to 1. If I want to do that, so I put I equal to 1 here. That means, okay, so it will be 1 multiplied by delta 1, 1. And we remember delta 1, 1 is 1 because it's still on diagonal and these indexes are exactly the same. And so plus b2 multiplied by delta, we decide that will be 1, 1, 2. But 1, 2 is 0, so this term falls. And then the same with b3, so we have delta I3, and delta I3 is also 0 because they are not repeating here. So if we want to write the components correspond to I equal to 1, so the only thing that will remain will be b1. And exactly the same, similar will be for 2, so only this term will survive, and for 3 only this term will survive, and actually only b3 will survive as here b2. And we can say that all the thing is nothing but bi, all the components of bi, right? So basically that will be b1 when I equal to 1, b2 when I equal to 2, or b3 when I equal to 3. So that's the definition of our components, bi in index notation. And finally, we can properly get back to the our trivial components of any vector as again using this projection operator. But now what if we want the components in our coordinate system, so we project it on our mutually orthogonal unit basis vectors E. Right? So that's what we will do. So here is some random vector A. We want its components in our Cartesian coordinates. So what we do, we just multiply it as a scalar product, because that will give us the projections on these directions. All right, that of course makes sense, right? And so we can now continue and write it explicitly. So EI I don't need to deal with, but A I want to write it in terms of its components, and we remember this will be a linear combination, right? So again of the components, and project upon the directions that defines our coordinate system. And so again, so we just put here AJ outside, and then deal with the multiplication EI dot EJ, and we already know that this is delta IJ. One more note here, of course, you know that when we calculate this projection, this is as a dot product. Here, the order of our multiplication of two vectors, scalar product or dot product of two vectors, doesn't matter. So we basically will get exactly the same number, scalar, when the result of that multiplication, if we change the order, if we multiply A with EI. But of course, you know that other types of multiplications will not follow this rule, so we'll need to be more careful about the order. Here, the order is not important, and of course, that's either projecting one vector on another or the other one on the original vector. Will be yielding exactly the same result. Okay, so let's continue with that and finish this this exercise. So we can pull this AJ outside and multiply EJ, the dot product. This is by definition our Kronecker delta, so we can replace it with delta IJ. And then again here we can exercise our rules that we just described here when delta acts on some quantity here. So when you see the indexes that they actually repeat here, so then what delta actually does, and we've seen this in this example, is that because of its structure, we can just replace the index here with the free one, and so the result will be A1. And so this is of course a trivial result, so you wanted to know what are the components properly of that vector, and so that's how you would do that in the proper manner. You calculate the projections, and of course you obtain these components that we started with. All right, so now we are through the scalar product, and the next order of business would be vector product. Again, things that you already dealt with in this way or another. And and before we're going to go into that, so let's introduce another symbol that is also will be very useful for us in certain cases, which is called the permutation symbol, or Levi-Civita symbol. This is the name of the person, Italian scientist, who gave his name for this symbol. It appears to be very useful for us. Okay, so let's just jump into that, define it properly, and then see how we can use it in our, for example, vector product of two vectors. All right, so let's say, and you already can see how we are going into the vector product. Let's say we have this multiplication vector product of our familiar guys, of our mutually orthogonal basis vectors. So okay, so let's have a JK here. So again, at this point we are free to choose this, but they need to be consistent with our definition. And so this is the vector product of this, so meaning that what is here in the parentheses is another vector, right? We don't know yet what it will be. Also, we already have all the tools from previous courses how to calculate that. But what I want to do here is I don't want this vector just yet. I can reconstruct it if I want. I want this the components of this, calculate the components of this vector. And how we do that? So again, this in parentheses is some new vector, and to calculate the components, what I do, I just project it on my basis on our axis, if you like, in our Cartesian coordinate system. So dot product with the basis. So that will give us the components of this multiplication. Now we can do this manually, or we can just trust it at this point and see that this multiplication will work in a certain way exactly like that. So it appears that it will be this. The result will be 1, right? When I, j, k will be exactly in this order 1, 2, 3, or continuing from here 2, 3, 1. So I'm returning here. So let me just maybe draw this. So when we go with in this direction and have 1, 2, 3, then, and this is the direction of our going, so we have positive, a positive sign here that will be going 1, 2, 3, or we start from 2, 2, 3, 1, we're going here, or we start from 3, 3, 1, 2, then the result here on in this combination is will be 1. However, if we go in the opposite direction, okay, I will try to sketch in this opposite direction, right? So again, let's put the same numbers here. Then, as a result, we'll have disregard that will be negative. We'll have a box for negative. And so let's take an example. So we're going into the opposite direction. In the circle, we have 3, 2, 1, or we start from 2, we continue 2, 1, 3, and from 1, 3, 2. These combinations will provide us negative 1, negative minus 1. Anything else will be 0. So this complicated pseudo third order tensor, it's not a tensor, just a symbol, right? So it represents components. It doesn't, you see it's not bold. It's called, typically is denoted by epsilon. So this is Levi-Civita or permutation symbol. And so again, so when we have ijk's that are all different, so the combination will be either 1 when we have positive direction, or negative minus 1 if we have an certain negative direction. If they will be repeating, doesn't matter where and how, you will have 2, 2, 1, 1, then they will be 0. And that comes exactly from the rules how we do the vector product, and also from the fact that they are mutually orthogonal, right? And of course they are unit vectors, so that's what we obtained here. All right, so then what we are going to do here is use this definition to define our vector product. And you already can see that we can actually use that structure here as if we have already two vectors, and just the only thing that we need to add to that is the components of that vectors that we want to multiply. So this of course remains the same as we defined our coordinate system. Okay, yeah, and just to connect what we started with, the picture of Einstein actually appeared to be friends with Levi-Civita, an Italian guy, and so that's a comment of Einstein saying that there are he named just two things about what he liked about Italy, naming spaghetti, and Levi-Civita, that very smart and brilliant guy that he liked to interact with. Okay, so let's take this product, right, the permutation symbol or Levi-Civita symbol, epsilon, and use it for our vector product. And so, all right, so as promised, so we are looking into the multiplication vector product of A and B. So this is still a vector. This is also a vector. Vector product would produce that a vector, but here I put the index I, meaning that I'm looking into the components of this. And how do I do that? So this is not a vector already. It will be components, different components of I. So that I wanted to indicate. And the way to do that is to take this vector product and multiply it with EI. So that will produce the components. Again, the dot product will give us the projections, meaning the components, as we already have seen that. And here we just wrote explicitly our linear combinations based on our basis vectors of course with the components. And okay, so now so to be consistent with how we defined our Levi-Civita permutation symbol, and not to be forced to replace in indexes, so I'll just keep the same indexes here, JJ, and here KK, and here I. So then I can just notice that there will be a similar things that will come from this combination that we just described or defined our Levi-Civita symbol, right? So again, so here what we need to briefly look into and separate what we can easily we don't need to deal with and what still is important here. So scalars are A, J, B, K, so they're going outside, we don't need to deal with them at the moment, but with this dot and vector product we need to follow all these rules. So let's separate them, right? So we pull out of the parentheses these scalars A, J, B, K, so they're not bold, they're not vectors, but with vectors we need to be careful, so we wrote them, we still keep and need to treat them. Okay, so there is a vector product EJ, EK, so it came exactly from here, that's what remained in these parentheses. And so we this new vector is multiplied by, okay, dot product, again, projection, so EI. And this is exactly, so this is a structure that we wanted. This is our definition of the permutation or Levi-Civita symbol, right? So then we can just replace that, and so, and what we see, we have epsilon ijk multiplied by aj and bk. Now the components of that, so right, so we explain, so this is another vector, so the components, we had to have one free index for the components, so it's a new vector with new components, and so, and yes, here we do have a free index I, as the JJ are repeating here, meaning there should be a summation, must be a summation, and so, and KK, so there is another summation here. We have basically two summations here, but we still have a free index, so that everything makes sense. A multiplication of these two produces the vector, so the components, free components, that will be for I, there will be for I equal 1, 2, and 3, so there will be 3 components, and that the free index I here exactly produces it. Okay, as a reminder, right, so epsilon ijk, we don't need to calculate it many times, so it's already calculated based on the consideration of the properties of our basis vectors, right? Again, we have only combinations, only 6 combinations that are non-zero. Now with that we can write what are the components one by one, what the components actually will be in terms of the new vector, in terms of the components of the original vectors A and B. And so naturally we start from the component 1, right? So and so what does it mean? So we go here and we basically say I is equal to 1, so we put epsilon I and then jk, and that will be summation. So now we go here to the definition of Levi-Civita and try to find this that we start with 1 that are non-zero, and I have 2 combinations here, this 1, 2, 3, right, and the other one is 1, 3, 2. So one will be component will be with 1 plus 1, and the other one will be minus 1, so we'll have a plus and negative component. Okay, so the one that is positive is j equal 2 and k equal 3, so I come here and assign j equal 2, so a2, and k equal 3, so b3. So the first term in this summation will be plus 1 a2 b3, right? Right, so okay, so this first step, and then now the first component here, and so now the first component from this summation that is non-zero will be this one, j equal 2, k equal 3, substituted here. Then we have the one that is with minus and comes here, and then j will equal 3 and k equal 2, so that's you substitute j 3 here and k 2 here. And so this is your component 1. So, and this is again similar. You can also that's what you obtain in linear algebra when you calculate the determinant of that matrix with AJK and calculate the components of the vector product. So there are different ways to do that. So it can be also done in this way, but if you want to keep and we want to keep the index notation here, so these are the rules for the vector product. We would use Levi-Civita symbol. Okay, so with that we can do the same for vector 2, right? So component 2 of the same new vector, that is a product of our vector product, right? So A and B. So in the component 2 will be so instead of 1 here we'll have 2, so we'll need to go to this matrix of Levi-Civita matrix and see and look for this that start from 2. So we'll find 1, so that the positive 1 will be with j equal 3, a and k equal 1, so we'll have a3 b1, so will be positive, and a1 b3 will be negative. But let's check. So that's exactly what happens. So you can practice with that briefly, and so that machinery work very nicely. Okay, so the last example you can also do yourself if you like. You can pause this video and do that, but you already see the logic and you also know the result. So you're going back here, you need to find the component 3, meaning that I is equal to 3, right? So need to find these that start from 3. So here we go, 3 1 2. So we'll have positive a1 b2, and we'll have negative a2 b1. So this is the combination, and of course you already seen the result. You arrived at the same result of vector product in a little bit different way, right? Okay, so one more exercise is to just kind of practice and check yourself, is to look again in this our previous formula 110 and recall which indexes are free and which are dummy, so on which we're doing the summation, and which is free, and what component do we have here. All right. Let me just change the notation, and at this point we are done with the our consideration of vector, and our next order of business will be to looking into higher order tensors. So we'll of course go to second order tensor, and we'll consider what is there that we already know and what is there that we need to define and learn and start using that. See you soon.